reserved two spots for science, which is not exactly matter wave optics, but something from neighboring important fields. This is the first one of these talks, and we have the pleasure to have Professor Michel Heurs presenting us past, present, and future of laser interferometry for gravitational wave detection on ground. The floor is yours.
Now it works. Okay, so please let me know if I'm too loud or too quiet. Also, let me know if I go over time, because I do tend to get carried away if I talk about my favorite field, which is gravitational wave detection. So about the only thing you need to know about me is I'm a sheep in a wolf's pelt. No, I'm a wolf in a sheep. No, the other way around. I am a quantum optician working in the field of gravitational wave detection. And as you are all, I'm assuming from the matter wave optics field, you know about interferometry. So I'm able to skip quite a few things, which is great. But what I would like to do this afternoon, is to briefly show you some things about gravitational wave detection as we currently do it, which is laser interferometry based. I will omit a lot of things. If you have questions, I'm very happy to answer them, and I'll try my very best. Also about the neighboring fields, but please keep in mind, I'm a humble quantum optician working in the field of gravitational wave detection. So without further ado, I chose this title because I hoped it would make people curious about the talk and the field. This is a very selective view onto the past, present, and future of gravitational wave detection, quite obviously, from the view of a quantum optician. So to sort of start this story, I always like to show some pictures like this. So if you think about general astrophysics or observational astrophysics, then most people always assume we're talking about things that we can see with electromagnetic telescopes. And just to show you the progression of resolution and of the level of detail that we can get from these beautiful telescopes over the course of decades is this wonderful picture of the Eagle Nebula, the Pillars of Creation, seen as from the Hubble Space Telescope and with two instruments from the James Webb Space Telescope. And you can see that the level of detail and the resolution, depending on the instruments, obviously, and always this is in false colors, is just magnificent. And I'm not telling you anything new, because I'm sure as physicists you are all enthused by these kind of pictures. I personally, even though I dress mostly in black, I really like colors, and so I really enjoy I enjoyed seeing all the Hubble Space Telescope pictures when they came out, and even more so now that James Webb is active. So the electromagnetic spectrum, again, telling you nothing new, this is carrying owls to Crete, I guess, not owls to Athens, is for the human being, we see the visible range. And the reason I'm showing you this is because I would like to use an analogy. We, as gravitational wave detection people, whether we are observational people or theorists or data analysts or instrumentalists like me, we are standing at a threshold, just like Galileo Galilei did when he pointed his telescope into the night sky, because what he observed was the visible spectrum. And you know that that's only a tiny, tiny little bit of the spectrum that we can see over here. So within the visible, we see about an octave of frequency, right? But we have about 25 orders of magnitude in the electromagnetic spectrum. Okay. Should I be louder? Oh God, I hear myself very loudly, so I'm shouting at myself. Do you know? Okay. Galileo Galilei saw, and we with our eyes see an octave of the electromagnetic spectrum, of the visible, right? We see an octave. The entire electromagnetic spectrum that is to us, more or less, is 25 orders. Now, for those of you, again, you're all scientists, you know this, but I find it nice to visualize these things. So if you think about a grand piano, a Flügel, right? The grand piano has 7 1/4 octave, right? 13 white repetitive octaves, white and black keys. So 7 1/4. So you'd have to bunch 8 of those together and concatenate them one after the other to span those nearly 58 octaves. Right? So that's a huge spectrum that we can observe or could observe in the electromagnetic. And similarly, if we're currently seeing only very little of the gravitational wave spectrum, which is a completely different thing, then we still have so much more to discover. right? And just as observations in the electromagnetic spectrum have shown us it's the same object in different light, so to speak, we with gravitational waves are at the threshold of doing the same thing, because we have different machines at our disposal, of which some are already working very well and others have not yet shown any results. But we have a plethora of discoveries to make. Some of them have already been done, but it's only a small fraction of what we hope to see here, I should say, in the future. So just to remind you, again, I'm preaching to the choir here. So even though you are in matter wave optics, you probably know much about gravitational waves already. Just to remind you, they're quadrupole waves. So what they do is they stretch and compress space-time. So let me see if I can start this animation. Does it work? Yes, it's working. So if you imagine a ring of test masses, that's our favorite topology that we always use, then you can see over here that this ring of test masses is stretched and compressed periodically. So if I was that ring of test masses, I would be longer and thinner and shorter and fatter periodically if that gravitational wave goes through me. And gravitational waves are always produced when we have a non-spherically symmetric change of mass distribution. So whenever something happens that is non-spherically symmetric and it changes its mass distribution, and it should be significantly larger than me just hopping up and down, which would also be a non-spherically symmetric change of mass distribution, something of astrophysical wumms, then we would expect to be able to see gravitational waves or detect gravitational waves. So an event of that type is the type that we detected first, and that was in 2015. We published that in 2016, was the merger of a binary black hole system. And you can see over here, indicated in this animation, the Schwarzschild radii of two black holes, and they're merging. And if you look really closely, you will see after this last stable orbit, they will merge and become one new black hole. So binary black hole right now turns into a new black hole. And I could tell you a little bit about black holes because they're really cool and I'm fascinated by them, but I will save that because I want to make a point about some other things. So if you want to ask a few things about that, feel free and I'll try my very best. The thing that you need to remember is that these cataclysmic events in the cosmos are only very weak when we see them. If they were really close by, they would be stronger, but that would be really bad for us. So if they are far away and they happen, and we then, after a travel time of however hundreds of millions of years the gravitational wave takes at the speed of light to reach us, we then measure them, the effect is actually tiny. And I actually put that here in the animation at this point where I said a typical strain, the change of relative arm, so the differential change of arm length, delta L over the arm length baseline, is on the order of 10 to the minus 21 or smaller. That's pretty small. So this is one type of event, and we've measured these kinds of events many times now. The other really exciting type of event that we've detected so far is the merger of two neutron stars. So neutron stars, I always say, are what happens when there's not enough, when they're not big enough for black holes, right? Wenn es zum schwarzen Loch nicht gereicht hat, I would say in German. And when they merge, then sometimes, at least once, as we've seen, there is not just gravitational wave emission, but there is also emission in the electromagnetic spectrum. And we'd call this multi-messenger astronomy with gravitational waves. So what happened in 2017 is that we had one event called GW 170817, which we were lucky enough to see, where I'm going to repeat this. No, there we go. Where you can see that these black holes, this binary neutron star system over here, it's not wanting to run. You can see the white bluish lines, which are supposed to be emission of gravitational waves. And then after that, you see a whole range of emission in the electromagnetic spectrum. So over here, you see the gamma ray burst, and then UV light of the kilonova, and then in the infrared via the UV, you see all the and the last part is the X-ray emission that we're seeing. And there were observations all over the world, both on the ground and in space with satellites, of about 70 observatories that were watching this gravitational wave event in the aftermath. And they saw all this beautiful electromagnetic radiation, and there was this wonderful measurement campaign that went over weeks and months. And this was sort of the birth of multi-messenger astronomy with gravitational waves. Spoiler alert, maybe a little bit of a fly in the ointment. We have only seen one of these events so far. People were hoping that we would see these in our left, right, and center. They're not as common as we'd hoped they would be. But we've learned a lot from this one event already. So I have over here something that we call the masses in the stellar graveyard. Now, this is from the gravitational wave transient catalog number 3, which includes all the measurement data from the first 3 observation runs. And what you see over here, just visualized, is when 2 black holes, like blue dot over here and blue dot over here, merge and form another black hole, or when a neutron star and a black hole merge and form another black hole, or when something like 2 neutron stars merge and form something where we're not entirely sure, is it a very light black hole or is it a very heavy neutron star? So just to show you that we've seen many events, within the first 3 observation runs, we saw 90 events, which is pretty good. And now we can actually talk about gravitational wave astrophysics or astronomy. We're observing many events, and the more sensitive we get, which I'll talk about in the rest of my talk, the more events we can measure, we can detect, and the more information we can extract. We can actually do astrophysics, and that's our goal. So it was never about proving Einstein right. It was obviously a nice touch. Einstein was right again, but it was about doing physics, doing observational astronomy with gravitational waves, together with electromagnetic and neutrinos. So these observation runs I talk about, as you probably know, we have the now called advanced LIGO detectors, the advanced Virgo detector, and the Kagra detector in Japan. So LIGO in the US, Virgo is a French-Italian collaboration in Italy, and Kagra is a Japanese detector. And you can see over here from the first observation run to the now currently running 4th observation run, which we're in, the astrophysical range has increased steadily. And I'll show you another animation in a few minutes. So just to let you know, we always have observation runs, and then we take breaks in order to upgrade our instruments, fix broken things, but mostly make them more sensitive. And that's why the range increases in steps. Makes sense? Makes sense, right? Good. Okay, so I can see everyone's still here, charged on caffeine. We'll jump right in. So what have we already learned from these 90 plus detections? Because we're currently in observation run 4, and we have many, many new events and a lot of more candidates that we're currently investigating. So we obviously detected for the first time directly gravitational waves. Obviously, Heurs and Taylor did that indirectly much earlier, but for the first time this was directly detected. We've learned a lot about the physics of black holes and also binary black hole systems. We detected gravitational waves from a binary neutron star merger, in one case even with electromagnetic radiation. We can localize the gravitational wave source well if we have multiple detectors on the ground that can triangulate where the signal came from, which is a reason why we need more gravitational wave detectors. We tested general relativity again, measured the Hubble constant with what is called now a standard siren instead of a standard candle, not supernovae, but in this case, something that we can listen to, gravitational waves, ground-based detectors measuring the audio band. And we actually found out that there are black holes in 2 different mass gaps. So we detected types of black holes that were not anticipated from theory, which gives rise to a lot more investigation to come. So this is an exciting field with lots of need for new developments and more researchers. Shameless advertisement for people who would like to cross into a different field maybe. So as I indicated earlier, the gravitational wave spectrum is really, really wide. And you can see that the time scales corresponding to really long wavelengths from the start of the universe. So basically Big Bang or quantum fluctuations, whatever is your favorite denominator for that, all the way to nowadays we're even talking about gravitational waves in the kilohertz and multi-kilohertz range, maybe even higher than that. So we have all this beautiful source forest to harvest, but currently what I will be talking about are only the shaded areas, and of that only the sort of reddish shaded area, which is terrestrial interferometers. I will only at one point mention spaceborne gravitational wave detection, which is in my case mostly the LISA project, but I will stick to ground-based gravitational wave detection. There are also things like the pulse timing array, which had really cool results just earlier this year. Was it this year? Time flies. I think it was this year. And the cosmic microwave polarization, so the background of cosmic microwave background polarization, and that could be an indicator for different types of gravitational waves. So what we are talking about today is the global gravitational wave detector network as it exists at this moment in time. And that's the so-called 2nd generation 2G. And we have, as I said, 2 detectors in the US called Advanced LIGO, 1 detector in Italy called Advanced Virgo, 1 in Japan called Kagra, which is an underground detector, and a small gravitational wave detector in Germany, which is a German-British or British-German collaboration called GEO 600. And then there is another detector under construction called LIGO India, which will be constructed in India. The reason why we want a detector on the southern hemisphere, and it's just about on the southern hemisphere, we'd like more, we always want more as experimentalists, is you can triangulate better, right? The more evenly spaced your detector network is, the better your resolution is. So they all look kind of similar. They're all micros and interferometers, and I don't need to preach that to you because you know exactly about interferometer topologies. But if we take a slightly closer look into what they look like, I've made a simplified schematic of an advanced LIGO interferometer here, and we can look at a couple of I would like to show you a few of the advanced detector techniques that we employ in order to be sensitive enough, because as you know, micros and interferometers are old. Right? In the 1880s, Michelson and Morley did their famous experiments to prove or actually disprove the ether. So you can do interferometry with matter waves, which is really cool, really difficult. You can do it with laser light, but you can obviously also do it with adequately filtered normal light, right? You can just use a lamp and just filter it nicely spatially and spectrally and then do interferometry. And they had really amazing resolution in the 1880s already. However, we had to improve that by many orders of magnitude to get the sensitivity of this 10 to the minus 21 and better that I have been talking about. So some of the tricks that we employ are, we obviously use the best laser systems that you can build. We also use some so-called advanced interferometer topologies. Ask me about that later if you're interested. I've skipped that in my talk because it would take too long. We use suspended low thermal noise optics, which is something I will just touch on a little bit, and we use non-classical light. And that's a field I'm particularly passionate about because I work in the field of non-classical light, and so I would love to talk about it more, and I will. So if we look at the design sensitivity of advanced LIGO, and this is a design sensitivity curve, it depends on the parameters you choose. Those parameters are not necessarily all fixed, but this is a specific configuration which is very close to the operation. Which at the moment, we're not using as much power. This is 425 watts. Whoa, I didn't do anything. It's not me. 125 watts, we're using a lot less power at the moment. So what I want to show you, and it's probably again something that you know, is we have a lot of noise sources that are influencing our instrument. If these noise sources are uncorrelated, the total noise of the system will be the root of the sum of the squares. And that's exactly what's happening over here. So if you look at the black curve, which is the envelope, then you can see it's mostly dominated by the pink curve and a little bit by the red curve, and at low frequencies by the brown curve. And I would like to show you a couple of these limiting noise sources. So the thing that you need to remember, but it's obvious for you, I guess, is that it's all about signal to noise ratio. Anything that is below my black envelope total noise budget, this is obviously just a budget, not a real measurement, but I'll show you measurements later, is not accessible to us. So any signal that is below that is lost for us. So we need to push our sensitivity down. Lower detector noise is better, clear. So if you look at the effect of the observation range, the sensitivity on the observation range, you can see in this little animation that I picked out over here, hopefully it works. Where's my cursor? There we go. That wait a minute, sorry guys, and go. So that you can see that the initial LIGO range was 15 megaparsec. That was this little ball here in the middle. And then with advanced LIGO observation run 1, 2, observation run 3, and now observation run 4, we've increased our astrophysical range to about 190 megaparsec in design. I actually checked it just before the talk. It's around 170 megaparsec at the moment, where Virgo is currently hovering around 50 megaparsec because they're battling some problems. So you can see it's worthwhile. Every factor of 2 in sensitivity you can gain is great because you gain, it's all about amplitude in our case. So you gain a factor of 2 in this direction, and this direction. For me as an experimentalist, 2 times 2 times 2 is about the factor, is about 10. So no laughs? Okay, so too many experimentalists in the room. So every factor of 2 helps. Now, the design sensitivity of advanced LIGO, as I showed it to you earlier. Let's take a look at this brown graph over here, which is seismic noise. And I will mention that there is another part of seismic noise called gravity gradient noise, which I will not talk about today, but if you want to ask me, please feel free. This is what limits us at low frequencies. Actually, gravity gradient noise is really bad at low frequencies. So what do we do about that? It's seismic noise. Our test masses are moving. They shouldn't. They should be freely falling in space-time. And we do that by taking our test masses, which actually look like this over here, this little glass block. It's a fused silica block. This is at GEO 600. And you can see over here, this is a different fused silica block. Over here, the coating on it is, by the way, is first contact. It's just a protective coating like nail polish to protect the front surface during mounting. So these huge glass blocks are our test masses, our mirrors. And they are suspended from pendula in order to decouple them from seismic noise of the ground. And that makes sense, right? You take a mechanical oscillator and you look at it and its transfer function and amplitude looks like this, right? So at low frequencies, it shakes just like your excitation. At intermediate frequencies, at the resonance, it will shake a lot. So please stay away from the resonance. And then above the resonance frequency, that movement falls off as 1 on f squared. That's the mechanical susceptibility of your system. And that's great because our resonance frequencies for our pendula at advanced LIGO lie below 1 hertz, at 0.64 hertz to be exact. So if you cascade pendulum to pendulum to pendulum, if you have a four-stage pendulum suspension, you get a 1 on f to the 8 suppression of your seismic noise for frequencies above that resonance frequency. So for anything above, let's say 50 hertz, your test mass is basically free falling in space. But anything below that is not good. So if you want to see this in a more schematic version, you can see here the advanced LIGO suspension, and you can see it's sufficiently complicated. I'll just skim over this. One thing I would like to mention is that none of this is arbitrary. Everything is designed down to tiny little levels because you have thermal noise that is making your life hard. Thermal noise is like a hydra. It has many heads and different ways of turning up. And if you want to know more about that, happy to answer questions as far as I can. So the geometry for the next generation of gravitational wave detectors, because if I say we're at the second, it means we're working towards the third. That's what I'm working on, is what do we do with these test mass suspensions? Do we build them higher, just like Virgo does? They have 7-stage suspensions. Seven. They're huge. They're 17 meters high, 17. Or do we nest them? Do we make inverted pendulum, normal pendulum, inverted pendulum? Really complicated, but really good. That's what our Kagra friends in Japan are doing. Or do we also additionally have to go cryogenic for thermal noise reasons? The answer is yes. If you ask an or question, the answer is always going to be yes. We're doing all of these things. So to up the ante a little bit, the design sensitivity of advanced LIGO doesn't show any laser noise. Why? It's a trick question. We build really good lasers. Not me, my colleagues and friends build really awesome lasers and stabilize them really well. And I used to work in that field and I have the utmost respect for them because it's painful, trust me. But they build such good laser systems that in this noise budget, the laser noise doesn't even turn up, neither in intensity, nor in frequency noise, nor in spatial fluctuations. And if you want to see what they look like, these lasers, they're not off the shelf, unfortunately, but we do use some off the shelf components. And this whole table over here with some colleagues of mine in bunny suits is basically this part of the laser system. So this is this huge optical table, and it's a master oscillator power amplifier system with, at that time, 3 stages with 2 amplifier stages. They've now actually changed to another different amplifier stage, which I'll show you in a sec. And then the light is also filtered spatially by these 33-meter round-trip length mode cleaners, suspended mode cleaners. If any of you are interested in intensity noise, then this would be a little delicacy, I guess. If you look at the relative intensity or relative power noise as is written, I like relative intensity noise because for me, RPN is not relative power noise, but radiation pressure noise. So relative power noise over here is on the order of, this is the free running in black. This is the in-loop stabilization, which tells you that they're really good at stabilizing stuff. But then you see over here the out-of-loop stability, and it's awesome, right? We're at the level of 2 times 10 to the minus 8 over a wide frequency band. So this really doesn't make a difference in our noise budget. And this, by the way, is the new Vanadat amplifier stage that has been installed in 2018, I think, at Advanced LIGO. So if we go again to the design sensitivity, we've talked about the Brown seismic noise limiting. We've talked about the non-limiting laser noise. I've skipped quite a few things for time constraints. I would like to show you this pink curve a little bit closer. Now, I didn't make the graph. I did not choose the color. I do approve. This is quantum noise. And this means we have to delve into the quantum realm, which I hope you're happy and prepared to do. I chose a cat picture for that, as you do. And I would like to show you people who've seen me talk before know that I will show this abstract because I am in awe of this abstract. I really love the fact that my esteemed colleague Carlton Caves wrote an abstract like this, right? This letter solves the controversy. Quantum noise fluctuations matter. They do. Okay, so if I ever write an abstract like that, I think I'll never write an abstract like that. So what this says is that quantum noise is important in gravitational wave interferometers. And the funny thing is, if we're talking about 4-kilometer long arms with perfectly stabilized laser light, lots of power available, up to 200 watts of 1064 nanometer laser light. We're not using that much, but we could. And we have cavity in the arms of the interferometer, we have cavities. So there is an enhancement of power in those arms that we don't just have kilowatts, but we have megawatts of light there. And we're still talking about quantum noise, or we're particularly talking about quantum noise. Why is that? So let me show you how quantum noise manifests in the gravitational wave detector. You saw in this graph, this is just the same graph, just with a little bit of highlighting in it, that the quantum noise graph has two branches. One is 1 on f squared, falls as 1 on s squared, and the other goes flat. That's because we have two types of quantum noise manifesting, and that's just a consequence of Heisenberg's uncertainty principle. That's on the one hand, short noise, relative short noise. On the other hand, it's radiation pressure noise, quantum radiation pressure noise. And so these two graphs intersect at this intersection point. And if you change the power of the laser light in the interferometer, then these two graphs will move correspondingly and conversely. And the intersection point will run on this so-called standard quantum limit of interferometry line in orange. So you can see over here that if you decrease the power, it moves like this. If you increase the power, it moves like that. But you cannot access the curve underneath this SQL. That's not strictly speaking true. You can if you use signal recycling, but it's not easy to get there. And if you want a broadband reduction below the standard quantum limit, you have to pull a lot of tricks. And I'll show you how to do that. Okay? Just going to see if everyone's still awake and happy to be here. Yeah? Okay, cool. So, so what do? We use something called squeezed light. You might know this because you've probably worked with non-classical matter states of matter. And so you probably think squeezed light is really simple. And really the concept is. The problem is the execution is not really easy and squeezed states are really, really sensitive. So you have to be really careful when you produce and then use them. So the gravitational wave detector GEO600, which I will say has never measured any gravitational waves because it's too short and we don't have any arm cavities. However, we have developed a lot of technology which is used in the large scale detectors like advanced LIGO and advanced Virgo. And without us meaning the gravitational wave community in Britain and Germany, maybe other people would have made the same discoveries, but some of those discoveries from the GEO collaboration live in the large detectors. So we're part of that. And GEO was actually the first gravitational wave detector to ever use squeezed light as a routine instrument. Since 2010, we've been using squeezed light in the gravitational wave detector GEO600. And you see average-sized German men standing around, and this is the squeezing bench. The squeezing bench produces fixed quadrature squeezed light, which in our case is used to reduce the effect of relative short noise. So, if you look at this, this is the detector, this is the gravitational wave detector, and over here is the squeezing bench. These arms are 600 meters long. Over here is the output mode cleaner. Here is the actual photo detector to measure the fringes at the output. And over here you have your second harmonic generation to produce your pump light. Here's your optical parametric oscillator, which is some people call it an optical parametric amplifier. And then over here out comes the squeezed light and is injected into the output of the interferometer in order to block the open port for vacuum noise and produce a favorable coupling in the arms in order to reduce the relative short noise. And this is what you see over here in the blue graph and the red graph. You see that and this is actual measurements of the sensitivity of the gravitational wave detector. You see all these spikes, so that has to be a measurement, right? And you see that your sensitivity at high frequencies, which is the relative shot noise, by the way, folded with the cavity transfer function, which is why it's not white noise as shot noise should be, but it's folded with the cavity transfer function. This relative shot noise over here is reduced by the injection of radiation pressure, by the injection of fixed quadrature squeezed light. Now, the whole thing is a slightly complicated setup with it's got 3 laser systems and more than 200 optical elements, and it looks like this. But if you look at the schematic, you can see the really important bit happens over here. This is the optical parametric oscillator. Now, you may ask yourself, if I put in fixed quadrature squeezed light, I reduce my relative shot noise at high frequencies. What happens with my radiation pressure noise at low frequency? Shouldn't that come up? Because the effect of introducing squeezed light at fixed quadrature, phase quadrature squeezed light, is just the same as if you would turn up the power. Turn up the power, your radiation pressure noise will go up. Look at what happened. Geo is not sensitive enough for that at low frequency. Used our squeezed light source was put into wave detector advanced Virgo and ran there routinely in order to increase the sensitivity at high frequencies. So here's your sensitivity of advanced Virgo at high frequencies, and introducing the squeezed light source gives you an increase in sensitivity from black to red. That's pretty cool, right? Yeah, everyone's still awake? Good. Okay, awesome. So this is really cool. If you put in the wrong type of squeezed light, amplitude quadrature squeezed light, you actually get a decrease in sensitivity, but that's exactly, it works as designed, right? You're making it worse, so it should turn worse. But what happens on the radiation pressure side, pressure noise dominated side of things? If you look very closely over here, you really don't see it, because for both, it seems like the noise just goes up. So what you have to do is you have to focus in really tightly into this part and normalize to shot noise such that you can see things much more clearly. Then you look very closely. And if you now introduce the correct phase at high frequencies, it gets better. At low frequencies, it gets worse. Now, I hope I've primed you enough for you to enjoy this as much as I do, because you would think to yourself, now we've made it better here, it's getting worse over here. Isn't that terrible? Well, on the one hand, it is, because it means fixed quadrature squeezed light only gets you this far. On the other hand, this is an example of macroscopic quantum optomechanics. That's amazing, right? Because what we have is that the phase quadrature squeezed light reduces the relative shot noise, as it should, but it also increases the quantum radiation pressure noise at low frequencies. And what that means is that these macroscopic mirrors, they are over here, about 42 kilograms heavy, 35 centimeters in diameter, 20 centimeters in thickness. They weigh 42 kilograms. We change our photon statistics just this little bit with the squeezing. And this is all modified vacuum fluctuations, right? It's a whiff of nothing. And it makes these heavy mirrors shake more. Isn't that cool? I mean, it boggled my mind. I talked about this for a year and I just couldn't contain my excitement, because we're actually seeing the effect of modified quantum noise, of vacuum noise statistics redistributed on a heavy mirror. And if that doesn't make your heart sing, I don't know. It made mine sing for a long, long time. However, it puts us in a bit of a dilemma. We can't use fixed quadrature squeezed light anymore if we want to see a really broadband reduction of noise in our detector. So now we need to have something that helps us at high frequencies, like the fixed quadrature squeezed light did before, but also helps us here. So what do? We introduce something called frequency-dependent squeezing. This is even more complicated. However, it's a really nifty technique where you take fixed quadrature squeezed light and you reflect it off a detuned optical resonator, thereby introducing a phase shift that is frequency dependent. And so now, if you take a close look at this, you can see that you this is the frequency independent squeezed vacuum as we did before. Now we're introducing frequency dependent squeezed vacuum. So for high frequencies, we introduce phase quadrature squeeze light, where the uncertainty is reduced in phase quadrature and increased in amplitude quadrature. And at lower frequencies consecutively, we turn it more into amplitude quadrature squeeze light, where this width is decreased and this width is increased. And if you do that, you actually get this result. These are the two advanced LIGO detectors in Hanford and Livingston. They're about 4,000 kilometers apart, and they are built pretty much identically. And you can see over here, without squeezing the black curves, with fixed quadrature squeezing, which only helps in high frequencies, the green curve, which makes it much worse at low frequencies, in purple with frequency-dependent squeezing. You probably don't want to know how much work went into this. If you want, I can explain a bit more over dinner, maybe. I didn't work on this. I just admire my colleagues who did this. It's amazing. But because I'm already very advanced in my time, I just want to leave this part as it is and tell you, this is not the end. This is just the start of a new era of quantum-enhanced gravitational wave interferometry. And it's absolutely amazing what people have done. Again, ask me over dinner. I would like to take you on to the next generation. Yes, I'm a nerd. I really would like to show you the worldwide detector network of the future. Because as I said, we're in the second generation, we need to move on to the third, because more sensitivity means more astrophysics to be done and discovered. So this is what we have now, and this is what we will have in the future, where the one with the little question mark is an Australian detector. I would really love for us to have an Australian detector, because that would be firmly on the southern hemisphere and we could have even better resolution. Also, they have some really cool ideas. The one in the sky is the laser interferometer space antenna. That's the only mention I will make of spaceborne interferometry. And this one is the one I would like to talk about. This is the Einstein telescope. It's a planned European detector that I will lose a couple of words about now. So if you look at the sensitivities of the third generation of gravitational wave detectors, there was, sorry, maybe I should go back slightly. There's one over here called Cosmic Explorer. This is going to be an above ground on the Earth, 40 kilometer, probably 40 kilometer microson interferometer. So it's going to be 10 times as long as the advanced LIGO detectors. The Einstein telescope is different, but it's also a third generation detector, and we will work together. So if you'd compare the sensitivities, you can see over here in black the advanced LIGO doing, this is I think 02, so this is an older sensitivity, it's a bit lower now. And then you can see the design sensitivity, which we're approaching now in observation run 4. And you can see that the Einstein telescope over here, ET, in red, has a much increased sensitivity. Our benchmark for going from one generation to the next, oh, thank you. Really? Okay, I'll have to hurry up a bit more. Is about a factor of 10. You can see at low frequencies, it's more like a factor of 100 or more. So if you look at the astrophysical reach for, in this case, an equal mass, non-spinning binary wave, so in this case, probably a binary black hole, because huge masses, you can see that advanced LIGO in blue will be improved by a lot in reach. And in particular, so the red is Cosmic Explorer. And you can see, especially for heavy events, which might mean low frequency events, the Einstein telescope will be superior, really, really good. The reason why I'm so enthusiastic about this is because I'm, from the depth of my soul, a convinced European. I really like the idea of Europe, and I think it is a good thing that we're making a European project to draw us all closer together. That's all I'm going to say about politics, but it was an important point for me. I really enjoy the fact that we're working in a collaboration with many, many nations. It's difficult because people have different interests and different national interests, but it's really worthwhile. And it's something where we can really collaborate on an international scale. And it's going to be a very advanced detector, an underground gravitational wave observatory at probably 200 to 300 meters depth with 10 kilometers arm length. The reason I put a triangular with a little asterisk is that the topology is actually not yet entirely fixed. We have always planned for a triangle, but you never know what happens. So I'm going to skip over many things just to save some time and tell you that a lot of the enabling technologies, this was from the S3 roadmap proposal or defense. Many of the technology that we have to develop are things that we are actually concerned with in our community already. So for the low frequency part of the Einstein telescope, this is a lot of cryogenics, silicon or sapphire test masses, different laser systems. And for the ET high frequency, because the sensitivity is going to be split up into two different buckets, sensitivity buckets, where we split the difficulties of the high frequency and the low frequency into two separate interferometers, which will contain different technology to tackle both difficulties at the same time. The Einstein telescope, this is an old slide because the numbers are really, really outdated, will probably cost more than 2 billion euros, milliarden, not, so thousands of millions, not millions of millions. So these cost numbers are outdated, but it will be an infrastructure that will run for 50 plus years. Construction time is about 8 years, and we hope to have it finished by the late 2030s, maybe 37-ish. That would be my hope. And then we'll be sort of on par with LISA. And the site is not decided yet either. There are two candidate sites. One is in the tri-country area between Germany, Netherlands, and Belgium. One is in Sardinia, or on Sardinia, and one is potentially the third or second and a half one is in Lusatia. And I'll talk about that in the 2 remaining minutes I have, but not without leaving you with the science that we can do with the Einstein telescope. You might think that we've seen a lot of events, and we have, but we haven't seen all types of events. And there's a lot of nuclear astrophysics that we can do. So looking at the equations of state of neutron stars, which are basically just huge nuclear labs in the sky. We can't do that in the lab, right? So we've already constrained a lot of things in already of our measurements that we have now, but there will be a lot more. So the astrophysics and the fundamental physics and cosmology we can do with the Einstein telescope is amazing. The take-home message might be that we should be able to see basically all binary black hole systems back to the Big Bang. We should be able to see nearly all binary neutron star systems all the way back to Big Bang. We will see many supernovae, which I'm particularly excited about because we haven't seen that yet. It's very unlikely that stars will explode in a perfectly spherical symmetric way. So we should hear something like from a supernova, but we haven't yet. And what I really like is the view to the dark ages. We're going to be able to see back to redshift of about 100, which is a long way away or a long time away. But most importantly, the Einstein telescope is a discovery machine. So we'll probably see sources that we have not yet anticipated and hence not modeled. And if we see that kind of stuff, then we're really in new territory and we get new physics, okay? So with that, I would like to use the last minute. My watch says 41.2. So this is, I was talking with people over lunch and mentioned the German Center for Astrophysics, and people seem to have heard about it, but might not know about it very much. So I'm just gonna shamelessly tell you about this briefly. There is a German Center for Astrophysics called Deutsches Zentrum für Astrophysik, an initiative of the German astrophysics and astroparticle physics community. And 2 years ago, nearly to the day, well, not nearly to the day, we were funded from the German federal ministry. And this is a large measure to increase socioeconomic, to enable socioeconomic change in the far east of Germany, in Saxony. So we will build a center in Lusatia, which is in the far east of Germany, in Saxony, with, in the end, about 1,000 people working there, probably 350 scientists, and working on astrophysics and data sciences and technology. 2 scientific pillars are the Square Kilometer Array, which is a radio telescope array planned and already partially operational in South Africa and in Australia, and the gravitational wave detection of 3rd generation, which is in our case mainly the Einstein telescope. The concept rests on 3 pillars, which is astronomy. We currently have these 2 huge pilot projects, SKA and ET. Instrument science, which will be aimed at these projects, but also at other projects. And in the course of this center, which is aimed to be a permanent center, will grow and be a bit more fleshed out in terms of scope, and sources and facilities for data-intensive computing, such as green computing and smart computing. And I will leave you with an image of some of the friendly faces of the people I work with in the DZA context, and the last slide will be from my group. I have the chance to talk about the work that I have an amazing group of about 15 people right now, but if you want to know about that, again, ask me over dinner. So these are the people from the DZA. This is Günther Hasinger, our founding director, and a lot of this data people, people from technology transfer from all over Germany, currently working together in the DZA. And this is my, oops, that was wrong. And this is my lovely group. So thank you for your attention, and I'm happy to take any questions.
Thank you very much, Michel, for this beautiful talk, Ernst.
Thank you. Yeah, indeed, a beautiful talk. About the strategy of all future detectors, would it not be to be detectors the same frequency band, because you want to correlate them anyway, and not to frequency on the higher.
Oh. As in one. So firstly, all the ground-based gravitational wave detectors I mentioned are more the same frequency and in the high frequency range right yet. If you think about if you're asking about the Einstein, well, Cosmic Explorer is one detector, one large detector, and it will only have one arms. We will, with the one. I mean, if you look at this over here in the picture, you can see there are in each detector. But the Zoom window just popped up. Hopefully people are still connected. So over here, you can see, let's say the red detector has a dash detector and a solid detector. And that's one is the low frequency one and one is the high frequency one. They will live in their own vacuum envelope, but they will be in the same tunnel. And yes, there are difficulties with having co-located detectors due to correlated noise, you're right, but there is also something, we have a null stream because of the 3 individual detectors where you can actually subtract quite a bit of noise. And I will not answer this as a definitive, because there is indeed still a lot of discussion about the drawbacks of having co-located detectors and the advantages of having co-located detectors. And there is a huge study that has been done, the so-called cost-benefit analysis, where the topologies of having 2 Ls in completely different places in Europe versus 3 Vs at one location. So this is a difficult question, but also a very relevant one. Was that about what you wanted to know? Good.
Is there a date for the ET decision?
There are many dates and they always seem to shift like large projects do. It all hinges on finances. So on the pledge of different nations, amongst them Germany. That still has to, there's currently a prioritization process running in Germany for large, for the roadmap for large infrastructure. Everything above 50 million euros needs to go via that. So I can't tell you a number. We were hoping for a site decision by 25. Now it's probably going to be 26. And construction will not start before 27, but I see this shifting even further.
So one of the fascinating things I find with the gravitational wave detectors is that you always seem to be detecting much more than astronomers think possibly possible, right? Which brackets cast some doubt on any of the cosmological predictions that people do, but never mind. Now, your sensitivity is going to go through the roof. You're going to go to very low frequency bands. At some point, will it not get too noisy just from the universe?
That's an awesome question, as all questions usually are, because they prompt you to think in certain directions, right? So I have a slide somewhere, but I'll not pull it up because it'll take time to find it. We can resolve a lot of binaries, but there is also a din, like noise from unresolved binaries. And it's all about our data analyst / numerical theorists to model those correctly. So there's indeed at the low frequency range, there is a sort of a wedge in the sensitivity where we will be able to resolve binaries, and then there will be an unresolved mess of binaries around that as well. So yeah, the answer is yes, it will be difficult, but the question is, how do we extract that knowledge from our data stream? Follow up?
Yeah, follow up, because does that mean that there's a limit to the bright gravitational background, if you want to? Does that set a limit to how big or sensitive you want your instrument ever to be?
There are two things about making your detector more sensitive. One is deepening the bucket, the sensitivity, we call it the bucket, right? The sensitivity curve looks like a bucket. We want to deepen it and we also want to widen it. So yes, in a way there is, however, this is getting into a realm that I'm not very firm in because I'm not a data analyst. So how we find things in our data is actually quite interesting. There is one thing that people do, and that's doing matched filtering. Basically, they look for fingerprints in the data, and that's when they have models of what the signal should look like. And if you have that, you can extract it. The things that are maybe even more interesting are the unmodeled sources, where you just look at the data and say, there's something statistically significant seeming in this data. And then you have to sort of retrofit what that could actually be. And in my opinion, they will find a way to take out that din from the data. Please don't ask me how.
Maybe just a short follow-up on this point, because I got the impression that maybe Wolf thinks that this is expected across all the frequency ranges, but it's mostly from white dwarf binaries, right? So it's just in a certain range of frequencies, but you happen to catch a little bit of the N with the low frequency part of Einstein telescope. Is that the point?
Yes, that is indeed also a very important aspect. I'm actually going to search for the graph that I have in my many backup slides. Is this a good one? I'm not sure if that's a good one, but it's the first one I found, and I can look for more. What you can see over here is you can see over here, this is LIGO, advanced LIGO, and over here is should be the LISA band, right? E-LISA and LISA. And you can see over here resolvable galactic binaries, and it's not a really good graph, but there's a bunch of unresolvable galactic binaries which would be here, and this would limit you in a certain range of your sensitivity, but not over everything. But what you can also see is that there are gaps where we don't actually. So this is pulsar timing, where the pulsar timing array is, or the idea of a pulsar timing array is amazing in my opinion. You have pulsars, and they're like lighthouses in the sky, right? They emit radio bursts, and if you're in their light cone, so to speak, you see a blip every time the pulsar spins around itself. And these are the most accurate clocks in the universe. If now you see this blip at, I don't know, kilohertz, that comes towards you and you can detect it, and if that stream of pulses has is disrupted, has a shift in it, a periodic shift, then you have to know that the travel through space-time of those pulses has to have been modified by the effect of gravitational waves, where space-time is stretched and compressed in between. So your pulses are stretched and compressed by the effect of gravitational waves. And if you see that or detect that, then you know that you have had a gravitational wave between the pulsar and you. And if now you have many pulsars, you can actually triangulate like that. I find that fascinating, but that's about the extent of what I know.
Hello, thank you very much for the talk. The 2 times 2 times 2 equals 10 joke was very good, even though there wasn't that much laugh.
It's late.
The question I wanted to ask was, when you're mentioning the trade-off between the shot noise and the radiation pressure, when we look at the shot noise, is if we assume that there are N particles that are being emitted, even from a purely classical analysis, you do get the variance as increase. If you increase the number of particles, the variance reduces in how you get them, and the pressure noise increases accordingly. My question is, I don't want to take away your excitement from the mirror vibrating, but isn't this phenomenon purely classical, or what is needed to make it a quantum phenomenon, given that a purely classical analysis of it would give us the same trade-off? We don't have really conjugate variables the same way that we have with position and momentum or other ones.
I'm hoping I understand your question correctly. So what we're talking about quantum radiation pressure noise?
Yeah.
And the effect of shot noise based on the Poissonian photon statistics of the light, right? So it's relative shot noise. It's always root n divided by n, right? And so that grows with 1/√n, shrinks, and the radiation pressure noise goes with root n. So the two do act conversely. This is, I think we're kind of at a point where people would differ on the question, is this quantum or not? Because we're talking about the photon statistics of a coherent state, right? For me, as soon as if I do give my lecture on non-classical light, I will say that if I reduce the variance in any quadrature, any arbitrary quadrature under the limit given by the vacuum noise, I have a non-classical state. And for me, that's quantum. I hope that kind of elucidates what oh, perfect. Thank you. I love thumbs up because they tell me exactly if we've communicated. Great.
All right. So I think we need to move on. Let's thank Michel a lot.
Thank you. And I would like to quickly say thank you so much for inviting me. I'm having a great time, and thanks for putting up with the exotic bird in the in the matter wave field. So I'm very happy to learn some more things from you.
Yeah. You have a USB-C? No, but I don't know. Yes, all right. All right. Good. Not good.